Hello, good morning. I am Jeet Verma, and today we will be studying the topic the curves. And I think it is really fascinating and important topics in computer graphics because with the help of curves we get smooth and accurate shapes. And with the lines we cannot achieve that. With straight line alone we cannot. So let's just start. What are we going to learn in this video? Introduction of curves in computer graphics, the representation of curves, the parametric curve representation, the basic terminologies of curve, the Bézier curve, the properties, and the derivation as well. Okay, let's just start. The curves in computer graphics. Let's we go for this, then we go for examples. Okay, used to create smooth and accurate shapes in 2D and 3D. Yes, represented outlines, object boundaries, and the motion paths. Also is defined using mathematical function control points. Yeah, how can we make anything in computer graphics without mathematical function? We cannot do anything in it without mathematical function. And in curves, control points are added too. Okay, offer more flexibility and precision than the straight line segment. Of course, that's what we talked about in the beginning of the video. Fundamental for modeling, animation, CAD, typography, and UI design was okay. And now we understand this. What is curve? Is like basic mathematical example of curve. We have already did the definitions part. We have 2 points A and B. Okay, you put your pen here. Okay, without lifting you go from A to B. That's curve. Okay, it doesn't matter what shapes you create. Like I created this one, it looks a little like curve. Okay, it's fine. But in second example, it does not look like curve, it looks like straight line. Yeah, but the thing is, it is also curve. Straight line is also curve because it fulfills the requirement we have told earlier. Okay, so now we have representation of curves. Curves are represented using mathematical equation set of point. Yeah, three main forms of representation: explicit, implicit, and parametric. Okay, first is explicit. Curve expressed equals to y equals to fx. Yes, in explicit curves, the best example we have is a line equation, which is y equals to mx plus c. So with that equation, we can see if we make a change in x or we put value of x, we get value of y. So we can see the y is kind of depending on x and x is kind of depending on y too, right? Now we have implicit curve defined by equation f x comma y equals to 0. So by looking at it, we also have an example of circle. Okay, so mostly, yes, we have example of circle. X square plus y square equals to r square. Okay, if you get if we change r into 5, so we are kind of saying it to computer, okay, this is the radius. Okay, now find x and y and draw it. But that process is not very smooth. In curves, smoothness is really important. Curve should be smooth. Okay, so now we have the hero of us, the parametric representation. What is it? X and y expressed as a function of parameter t. Okay, you get x, or they are saying x and y expressed as a function of a parameter t. They're trying to say x is kind of dependent on t and y is kind of dependent on t. Okay, the parametric representation is preferred in graphics for smoothness, animation, and control. In implicit, we do not have smoothness and control, but in parametric representation, we do have that. Okay, the parametric curve representation. What is it actually? The curve represented using parameter t. Yes, coordinate expressed as a function of t, xt, and yt. St changes, the point moves smoothly along the curves. Let's just understand it by the example. Let's just understand it by example. Okay, so we have this third example here. We have 2 points A and B. Now forget everything. You should know this curve is a path. First point, this curve is a path. Now second point, On this path we have a point. Okay, we have point. Now third path, the point is moving on a path. We have this 3 point. Okay, now we'll see it on the screen. When the value of t is 0, the point is on A, but the value of t is 1, the point reaches to B. So that's what I'm trying to say here, is as it the t changes, the point moves smoothly along the curve. That is why the curves are so smooth in parametric curve representation. Works naturally in both 2D and 3D graphics. If you want to make 3D graphics, you can do z equals to zt. It is a foundation of modern curve technique like Bezier and B-spline curve. Okay, provide smooth control and easy animation flexibility in shape design. That's what we talked about earlier. Now we have basic terminologies of curves. We need to know before going for the Bezier curve. What are the control points? What are the control points? Points that define and influence the shape of curve. Curve usually start at the first point and end at last. Curves usually start at its first point. Curve usually start at first control point and end at last control point. Okay. The degree of curve is actually control point plus one. What is convex hull? Convex hull have to actually cover all the control points, not just first. If you cover first and the last one, it would create curve. And if you try to contain all the control points, we create convex hull. Okay, and we know about parameter t. As you can see in this diagram, A to B is actually a curve. Okay, and this whole full these dash lines are convex hull. Okay, now we have Bezier curve. What is actually Bezier curve? The parametric curve defined using set of control points. Okay, uses Bryanstein basis polynomial to generate curve. It uses Bryanstein basis polynomial in the formula. Okay, we will be going for that later. Curve start at the first control point. Curve start at first control point and at last. That was the definition of control points, right? The intermediate control point influence the curve direction and shape, right? The degree of Bezier curve, number of control point minus one. Okay, provide smooth and easy controllable shapes. Yes, and widely used in vector graphics, local design, typography, CAD, and animations. And now we are going to take an understand one example. Okay, we have these 4 points. It is Bezier curve, by the way. Okay, it is also Bezier curve. We had a statement here. Intermediate control point influence the curve direction. Here, the A, B, C, D are all control points. A to B is curve and other is convex hull. Okay, if I put A to here and B to here, the curve will change, of course. That's what the statement was saying. So move to properties of Bezier curve. Start at first control point and end at last control point. We know that the curve shape is fully determined by its control point. Yes, the tangent at start follows the line from P0 and P1. We will understand that later when we do the derivation part. Okay, leave that another one too. Moving any control point affect the entire curve. Yes, that what we saw in formula. Provide a smooth and continuous shape due to parametric definition. Yes, the shape was smooth. The degree of the curve equals to control point minus 1. Okay, now we have covered the properties of Bezier curve, what Bezier curve would look like and everything. And now we have to understand first this. What is Bernstein basis polynomial? Okay, and now this. What is these two lines are trying to say? I do not understand anything. I know you did not do. Let's start. We have to go for the document here. Sorry, I was kind of forgot to open that one. Okay, so here the Bezier curve. Okay, and first we just go for direct, the Bezier polynomial function P0 to Pn, right? That's what we saw in the statement. This is a pu equals to summation of n I equals to 0 pi and Benz I comma n, and in bracket we have u, where the pi is a control point. Pi is a control point, and Benz is what? A blending function, Bézier function, or Bernstein function, right? What is it? Bernstein, basis of polynomial. Okay, it's kind of same. We use those, and where is it? Yeah, it is same as blending function. It's just other name of it. Okay. So what is the formula we have? Benz in u, this part. For this part, it's called blending function, and we did simplify it though here, and we also simplified the Bezier function into xyz coordinate. Okay, and we have actually find the Bezier curve for 3 points. Okay. If we have 3 points, like we said in a degree part, how to find the degree? Control points minus 1. We have total 3 control points, so it's n minus 3 minus 2, so it's we have degree of 2. It's nothing, literally nothing. We have formula, you put it there, summation plus plus, value of I changes from 0 to 2. Okay, and for this singular part we have actually solved this. We have this. Okay, so we did solve it and solve it. Okay, so solve it, it's normal permutation. Okay, and then what did we do? We just added it, the main formula. So that's what it would look like for 3 points. Okay, for 4 points it's literally the same process, but for 4 points we kind of did a derivation. Okay, how? Let's see. With the help of parametric equation, let's see. So that is a formula for 4 points. I don't believe it, I want to prove it, so let's just prove it. So we have this kind of Bezier curve right here, which we have 4 control points and we have points inside them. Okay, so first we find q0. So that is like normal formula, 1 minus u, and p0 p1 here plus u. This is a normal formula for parametric equation, and it will repeat. Q0 exists between p0 and p1, so that would be the formula of it. Okay, same for q1, which exists between p1 and p2. So we did root of formula or equation for it. Same with q2. Then we have c1 and c2. C1 is here, C2 is here. Oh, actually forgot to write. This is actually Q2. Okay, so yeah, this is Q2. We have found C1, C2. It's literally the same for everything. Now C2 has become midpoint. So the formula would be like between Q0 and Q1, like we did with P0 and P1. Okay, now for C2 we did Q1 and Q2, and we have R here. R has become the midpoint for C1 and C2. The formula would be like that. So what are we going to do with it? We have wrote all the parametric equation for all the points we have in this Bezier curve. Okay. So first we are going to write the midpoint of everything, which is R, like the midpoint of curve itself. Like this is curve, main curve, which is R, kind of tangent to. Okay, here. Then what did we do? We should put the value of C1 and C2 from here. I think I should change the pen color, right? Yeah, C1 and C2. So we put it, we multiply it, then we get this after multiplication, and we also did the sum of these two. We did sum of these two, and we put it the value of q0 here. Put it the value of q0 here. Okay, so we did put the value of q0 here, and we have the sum of those two value here, same as here. And then we'll write what the value of q1 and q2 also from the equations. So what do we get is this, and then we just add it. We do not have any p0. We do not have any p0. So what do? Just write normal p0 here. We do not have we have two p1, so we added them to make them 3u. We have two p2, so we make them 3us square. We don't have p3 value, so we just did what? Nothing. Okay, so we have this, we get this equation, which is, if you know, is actually exactly this equation. You can compare it. 1 minus u square p0, 3u, 1 minus u square p1. Yes, 3u square, 1 minus u p2, exactly u cube p3, exactly same, right? That's why we say the parametric equation are the foundation of Bézier curve, because of this, right? And what did we do with it? Nothing. We just put them in x and y coordinate. So thank you.